So yeah, this is joint work with colleagues from Oregon State University, and as the title suggests, we combined ideas from private information retrieval and private set intersection, and a use case for this is how to scale private contact discovery. So contact discovery, it happens whenever you join a social network and you want to find out which of your existing contacts are in that social network. So for example, you install WhatsApp on your phone and you have your address book with a couple hundred of people in it, and you want to figure out which of those people you can reach through WhatsApp. So what happens these days is that a very naive and insecure hash-based protocol is run, namely hashes of all your user contacts are sent to WhatsApp. WhatsApp checks if it knows these hashes and sends back the matching contacts to you, and then you know which of your contacts use WhatsApp. This is vulnerable to brute force attacks because you can simply go through all the phone numbers. It's a very small input domain. It takes a couple of minutes or hours, depending on the length of the phone numbers. Or you can even store these hashes that you receive and compare them later on when you learn new phone numbers. So even if your input domain is a bit more complex, say email addresses or something, once you know them, you can store them forever. And we think this is a use case where the privacy is very important, and the privacy of the user inputs and your contacts needs to be protected. And it also needs to be efficient and scalable, since you run this once when you join the network, but you also want to keep your the people that use this messenger, you want to keep this list updated, so you need to run this periodically. So what we propose and what as a solution is PIR-PSI, where we have a protocol in the middle that receives the user contacts from Alice, that receives the WhatsApp customers from Bob or WhatsApp. And then in the end, only Alice learns the intersection, namely the contacts from her address book that use WhatsApp. And as a side note, this is not limited to contact discovery. It's just one of the use cases how we motivate this work. But you can also apply this to this ad revenue tracking that we've seen in the keynote this morning. So this is a generic solution actually to a private set intersection problem. Which looks like this. So you have Alice and Bob, and they both have their input sets, and what you want to find out in the end is really just the elements that are in the intersection between the two sets, and nothing else about the elements that don't match. So whatever, your grandparents who don't use WhatsApp should not be leaked to the WhatsApp server, and all the billions of other users who are not in your address book should not be leaked to you, to the WhatsApp user, or to Alice in this case. What makes it so special is that the set sizes in private contact discovery, or in contact discovery in general, are very asymmetric. So the user input is just a couple hundred of people, while the WhatsApp database is in the order of hundreds of millions of users. And this is something that many of the existing PSI protocols do not account for, and where we try to optimize for in this work. Before I go into the details on how we actually achieve this, I first want to explain to you what PIR, or private information retrieval, is. And before we do it privately, we have to do it in plain text. So in this case, Alice wants to query a database at a given index I. So she wants to retrieve the position in the database at index I. So in plain text, she just sends this index over, receives the element at position I, so in this case YI, and we're done. But we all know the internet is full of bad guys, and they look at your conversation, and if this thing is happening in plain text, of course the adversary learns what Alice was interested in. So we can solve this by simply using TLS, and we're more or less done if we do this right. But the problem that PIR tries to solve is what happens if the adversary is sitting on the server side. Because eventually the server needs to know what Alice is querying for, and this is where PIR comes in. And PIR, if you write it down as a protocol, it looks like this. Alice inputs her index, Bob inputs the entire database, and in the end, all that Alice learns is the database at the specified index, and Bob, or the database, doesn't learn anything about the query or about the response. So these queries have to be oblivious to the database. The PIR that we use in this work specifically is a multi-server PIR scheme, more specifically a two-server PIR scheme. There's also work that is based mostly on homomorphic encryption. It works with one server, and you could basically exchange these and just simply use whatever your favorite PIR scheme. But we use a specific two-server PIR scheme, and this comes with a very important property that some guy talks about a lot, like a lot, and this is no collusion. So it's very important. I mean, he's talking about different kind of collusion, but it's very important in this work. This is an assumption that we need to make. These two servers over here, they do not collude with each other. Otherwise, the security and the privacy of the queries completely breaks down. Yeah. So how does this two-server peer work in general? Alice, again, has her index I that she wants to query for. And then she sends a query that is secret shared between the two servers. Each of the servers sends a response back. And in the end, Alice performs some operation, in this case an XOR, to reconstruct the plaintext block that she was interested in. To give you an example from a paper from Cho et al. From 95, and this was the original peer paper. So let's assume Alice wants to query the block at index 3. So this is her plaintext query. So only the third bit in this bit string is set. And then she chooses these two secret shared queries where Q1 is chosen at random and Q2 is the XOR of the plaintext query with this random query. She sends these two queries over. And now the servers perform a pointwise multiplication of each bit that is set in the queries with the database blocks. If you look at the responses, you see what the servers actually do. And then they send this XOR back. And if Alice now XORs the responses, the blocks that are not important, namely Y2 and Y6, cancel out because of the XOR, and only Y3 remains. And this is the block that Alice was initially interested in. If you look at this more closely, you can see that the servers don't learn anything about the query, as long as they don't collude, obviously. This very basic scheme has the property that the queries have a length of n bits, so the size of the server database. And if you now think about WhatsApp, which has several hundred millions of users, this length would be 100 millions of bits. And this is obviously something that doesn't scale in practice, and there are schemes that do better. And namely, the scheme that we use is built from distributed point functions. Now, this is a topic that is much too complex to explain in one slide, and I try to boil it down as easy as possible, but the details have to remain in the paper. This is work by Boyle et al. From CCS 2 years ago, and also from Eurocrypt before. It's called function secret sharing, the overall sort of domain where these distributed point functions come from. And they are very similar to these two queries that we sent, namely that this function evaluation is secret shared between the two parties. And essentially what happens is that you have very short keys. I denote them here with a lowercase k. And these have the length logarithmic in the size of the big database. And they get expanded in this tree kind of fashion into this bigger uppercase case, which then sort of correspond to these queries that we've seen on this previous slide. And with this DPFs, we can build PIR, strictly limited to 2 servers. As far as I know, there's no generalization to more than 2 servers by now, with a nice property that the communication is logarithmic in the size of the database. And on top of that, all of this can be instantiated very, very efficiently only with AES, which is built into CPUs these days. So we have a native instruction set for this, and this actually runs very, very fast. Another technique that we need in this scenario is something that we call designated output peer, where the output of the peer query doesn't go back to Alice, but instead remains at the servers. And for this, Alice needs to send a mask on top of her queries to one of the servers, who then blinds his response that he would send back to Alice with this mask, and he sends it back to the other server. And in the end, the second server XORs the 2 responses, and what he learns is the plaintext result that Alice was supposed to get blinded with the mask. This, of course, assumes that the servers behave semi-honest, so this is a limitation in this case. Now, what we do with this is something that for one element is called a private equality test. Namely, Alice now not only knows the index, the mask, but she also knows an element that she wants to test for, if this element is at position I in the database. So what happens is that she blinds this element with the same mask that she knows, throws it into a primitive called private equality test that checks 2 elements for equality, and then returns simply if the element X is the same element as the element at position Y in the database. This is the overall idea, and this generalizes very well to more than one element if you just do it multiple times. In order to find out what this index I actually is, because it doesn't fall out of the sky, we use a technique called cuckoo hashing that specifies for each of the elements, because Alice only knows telephone numbers, she doesn't know the indices yet. But these indices come from a technique called cuckoo hashing. And in our case, the servers perform cuckoo hashing, and this means that every element, so every contact in the WhatsApp user database basically gets hashed into a so-called cuckoo table. This happens iteratively until all the elements are in the table, and then we have to make sure that there are no collisions. So for each position in the table that is determined by these hash functions, there can only be a single element. If a collision happens, then we need to relocate. So element y1 was in there before, it gets removed, and yn takes the place. And then we have additional hash functions who are then used to shuffle things around until everything fits and there's only one element per position. In this example we use 2, but in the paper we actually figured out that using 3 hash functions is the most efficient way for our use case. So in this case y1 gets thrown into the second hash function, another collision happens, y2 needs to be relocated, and in the end everything checks out. Obviously it's an example, so it has to check out. Just to give you some numbers, this cuckoo table is roughly 1.4 times the size of the WhatsApp database, because you need to prevent these collisions, so you need to make a bit more space. And we have a cuckoo failure probability of 2 to the minus 20, which doesn't seem very much, but since this is a one-time operation, so the servers only have to do it once during initialization, this is fine, because you can simply retry if it fails, and it fails 1 out of 1,000,000 times, so this is actually fine, and it allows to achieve a much smaller cuckoo table, which in turn benefits the performance. And what Alice does in this case is that she just applies all the hash functions that there are to her input set. So actually she has her element xy, x2, and xn twice in her cuckoo table. The collisions don't match here because we just throw all of them in the private equality tests. For example, if you want to check if xy is the same as x1 is the same as y1, you would run 2 private equality tests for the second and for the 4th position of this cuckoo table, and the result would be if there's a match or not. In the full PSI protocol, we don't run this private equality tests on the entire cuckoo table, but we first use this DPF peer that I showed you before to extract a small amount of elements from this large table. And we also, I said that before, instead of this single private equality test, we run a full-fledged PSI protocol, which is much more efficient than running individual private equality tests. So to recap what the actual protocol does as an overview is, first the server do cuckoo hashing on their big sets, capital N elements. Then we run this DPF query to extract out of this big sets of several hundreds of millions of elements, elements in the size of the order of the small set of the client. And then we have to apply an oblivious shuffle in order to hide which of the hash functions was actually used. The details of that are in the paper. I can't go into detail here. And the last step is that we run regular, basically off-the-shelf PSI protocol. We use one by Kolesnikov et al. From CCS, I believe, 2 years ago, to determine the intersection. And this is efficient because in this case, both sets are in the order of the small set. So this is a couple of hundred elements, and this is actually very, very fast, much faster than running it on 1,000,000 elements. In order to make this thing fly, we needed to optimize the algorithms and the implementation a bit. One trick that we use is binning. So instead of running this distributed point function on the entire domain of the cuckoo table, we basically split it up in small bins and run separate DPFs on these smaller bins. And this we can do because the elements are basically distributed uniformly at random. This also allows for parallelization, so you can ideally parallelize this on as many cores as you like and as many bins as you have. The other optimization that we have is batching. So usually you have a lot of queries per bin, and instead of running these queries separately, we just throw them all together and do one single pass over the database, which is much more efficient than reading the entire database of 1,000,000 elements over and over and over and over. And another optimization that we came up with is using larger PIR blocks, which means that these DPF trees are a bit more shallow and they terminate earlier, and with each of the queries you not only get one block, but you get like a handful of blocks. You can always tweak this parameter But this allows for shorter queries and a little bit more computation in the final private center intersection. I can't go into the details here in this talk, but I think it's described nicely in the paper once you get the overall idea. Another problem that comes up is that both of the servers in the classical protocol need to know the database. So to work around this, because WhatsApp doesn't really want to share its user database with some other party that WhatsApp is not allowed to collude with, to work around this, we propose an idea that results in secret sharing the database with 2 other servers, and then the query that is sent to these 2 servers is essentially the same as before, just that Alice sends the same query to server 2 and server 3 in this case. And if you look at, and then this delegation step happens the same as before. The first one is masked. And what happens then is that if you do the math, and this is also in the paper, in the end, everything cancels out. And what the second server in this case holds is the element at position I masked with a mask, and then you can do the private equality test or the PSI protocol. So this is a very nice property that we hadn't seen before. Maybe it's in the literature somewhere, but we can actually use this to achieve something a bit more practical without having WhatsApp store its entire database on some untrusted server. At the end, I want to talk a bit about performance. So the numbers that you see here are for a client with 1,000 contacts and a server with 1 million up to 256 million contacts. It's benchmarked on a gigabit LAN on one machine with a lot of cores. The implementation uses 4 cores. And if you just briefly look at the numbers, these are 2 sets of parameters for the bigger data sets here. You can actually tweak these bin sizes and the PIR query sizes such that you either achieve a runtime that is always below 2 seconds up to 256 million elements, or you can always stay below 5 megabytes of communication, depending on what you want to achieve. In a mobile scenario, you might want to limit the communication because whatever, your traffic is almost gone or something. We also determined that the client computation in this case is less than 10% of the total, so we believe this is practical. And as I told you, you can sort of fine-tune this for your specific application scenario. You can really choose what you want to optimize for. In order to compare it with related work, this is for a client set of 5,000 elements and the server set of 2 to the 24 elements. And limited to 1 thread in this scenario. So PIR-PSI is up there. It's the fastest one, but it uses a lot of communication because that's the parameter set that we chose. The work up here is from PETS last year. And it's in this comparison, it's the most inefficient one. It's based on oblivious evaluation of AES circuits. The work here in the middle is based on fully homomorphic encryption and is able to beat us in terms of communication, but needs a bit more computation. And the work down here is based on essentially an OPRF based on Diffie-Hellman, which is super fast because you just need to send, has super low communication because you just need to send the client set, but is also a bit more expensive in terms of computation. And also these 2 works down there and up here have the big disadvantage that they have an offline phase, which is in the order of hundreds of megabytes or even gigabytes that need to be transferred once. So if you sign up for WhatsApp, you need to download a gigabyte of data in order to perform this private set intersection. To conclude, I've shown you PIR-PSI, which is a combination of DPF-based PIR with state-of-the-art PSI, and you can use this to achieve scalable and private contact discovery. We have a C++ implementation, which will be on GitHub very soon. It's not there yet. There are some other PSI protocols there, but PIR-PSI will be there very soon. And there are many more details in the paper that didn't fit in the 15 minutes. And that's it. Thank you very much.
Thank you. Questions?
I'm curious, did you actually implement the function of secret sharing PIR yourself, or was there a library that you used for that?
We spent quite a lot of time implementing that ourselves.
Right, because I've read that paper and I was like, somebody else will do that and then I'll use it.
It was quite a lot of work and it was heavy machinery on like vectorization, AS operations and SIMD, yada yada. It was quite some fun. Yeah.
So follow up then, do you think that there's more performance you can squeeze out of that? Because that's a relatively intensive piece of code to write. Do you think it could make a significant difference on the overall runtime?
We tried our best, but of course we're not perfect, so maybe there's someone else who can look at it and
sorry, let me rephrase. If you look at it in a sense of like trying to profile your implementation, is that the vast majority of the work? Do you think that if somebody was to work on optimizing that, it could substantially increase the overall efficiency of it?
So the thing is that at some point you need to touch the entire database somehow. And this is what really limits the overall performance. So if you want to do this on 1 billion elements, you need to go through a database of 1 billion elements. And I don't think there's much you can do about this except for tweaking the parameters here and there for your specific machine. But of course we thought about this, but I don't think there's a general answer to that.
Okay. So from that, do you mean, are you already pretty close to that, like, speed? Obviously, you have to read it off the disk. Are you kind of pretty close to that already, just with the computations you're doing?
Pretty much.
Oh, wow, okay, that's impressive.
If you touch disk, you've already lost.
Yeah.
Luckily, the database will fit in memory easily.
Exactly.
So one thing you said is the cuckoo setup you only have to do once, but of course, every time someone does a contact discovery, it changes the database because they're gonna they've just enrolled, their data needs to go in the database. And I mean, when Signal even, which didn't have hundreds of millions of users, considered using PIR years ago, they looked at how many signups they would want to have per second and how big the database is, and even if it only takes 2 seconds, there are lots of people doing this in parallel, and they decided that was way too expensive. So what is your, like, taking into account that the database updates very quickly and that new people are signing up in parallel all the time, how many users can you support with a given number of cores or something?
I don't have the numbers in my head right now. There are some numbers in the paper on how to change the server database, so these signups so people signing up for the network joining the database. You could think about doing it in sort of time frames of a couple of minutes and then rerunning it again, but of course then people would need to wait a couple of minutes before they can actually be discovered, stuff like that. I'm not aware of any very good solutions for this right now, but there's works you can sort of try to work around, I guess. Yeah.
Waited for after, but
Sorry,
there's a paper. So I guess when you have this PIR with the cuckoo hash thing or the cuckoo table thing, it's very important to get as much. The whole reason for the cuckoo table is to get it as densely packed as possible. There's a paper called 3.5-way cuckoo hashing for the price of 2 and a bit, which I think gives you. The idea is to use irregularly positioned bins, and you get it's a bit more out of your cuckoo table. Anyway.
Okay, yeah. You can tell me later and I'll write it down. Yeah, thank you.
Any question on this side of the room? If not, there's a final one over there.
So I have a nice question, but because you use PIR, this means that the client might learn more than simply the query he will do. So I was wondering if there is a risk of privacy leaks.
I can barely hear you. Can you?
Yeah. So because you use private information retrieval, sometimes in some private information retrieval schemes, the client learn more than the element of the database. So I was just wondering if there is a chance that you might leak some information about the database of other phone number of people that are not in the list of the client.
Yeah, so this is actually taken care of by the PSI protocol that we run in the end. So the result of the PIR queries stays in its masked form on the server side, and then the client only learns the intersection at the very end after the PSI protocol. So even if there would be leakage, this would be completely captured by the PSI protocol.
Final question.
I hope.
So just to follow on with that question, so if I just put every single number in the world, I will get to know WhatsApp's database, right?
Yeah, but this is like an inherent limitation of these kind of.
So do they generally rate limit you or do something like that?
That's what you would do in practice. Yeah, you would just allow a query for up to, I don't know, a couple of thousand elements. If you were to deploy this for contact discovery, yes.
Okay, thanks again.
Thank you.
Thank you all for hanging around until the end. See you guys tomorrow.